this very viscous fluid. Just like, say, very thick paint or very thick oil and drop little marble. The motion of that marble, because the highly viscous fluid is usually very small velocity, to where the velocity is small, so small we call it creeping flow. It's like slowly dropping down due to gravity. So the velocity is small. As such, the Reynolds number is small. With that kind of constraint, where Reynolds number is like less than 1, I can solve this equation that includes viscosity. And that solution was first introduced by a gentleman called Stokes. We're going to see his name again in another 2 lectures. That he not only come up with this equation of viscous flow, he actually solved it with pencil and paper, no computer, no calculator. Or a very limiting case of small Reynolds number, and the solution to that equation is obviously beyond our coverage in the introductory class. But if you have a sphere, what type of coordinate system you think you may use to describe this motion?
Polar.
Polar, very good. Cylindrical, polar, very good. Yeah. Not rectangular XYZ, because it's not appropriate. You take advantage of the 3-dimensional shape, which is symmetric. You use polar coordinate or so-called spherical coordinate. Yes?
Is that lowercase d diameter?
Yeah, I'm fixing my nomenclature. The answer is yes. Yeah, diameter. So the solution to this equation, which you will see, is very elegant differential equation, very intimidating. But it turns out for a limiting case of very small Reynolds number, it boils down to simply a pure analytical function of viscosity, diameter, and velocity. As such, if I use the definition up here for the drag coefficient, you will obtain something that looks familiar. What do I mean by that? What does that remind you of? That the drag coefficient, or something that loosely related to the friction factor, as a function of the Reynolds number, is 1 over the Reynolds number. Yes?
It's like for laminar flow on the Moody diagram.
It's like a pipe flow or Moody diagram, where on the far left, when the Reynolds number is less than 2300, it's an upside inverted straight line where the drag coefficient is given as the inverse of the Reynolds number. So they're cousins. There's some similarity. Although one is external flow, the other one is an internal flow. But when you think about it, the physics are similar. So this creeping flow is, well, it's a little bit limiting in engineering applications. So in most cases, flows are very turbulent in the order of millions of Reynolds number. But academically, this is a very limiting and also interesting case, just for us to reference to. So that inverted region where the Reynolds number is small, I put a label here just to remind ourselves that the velocity is tiny, and that marble in that viscous fluid is barely coming down very slowly, very tiny velocity. We call it the creeping flow. So that turns out you can obtain without doing an experiment, but again, it's not very interesting because most cases Reynolds number is not in the order of 1. Yes?
For that equation here, there was CD equals FD over 1/2. Yeah, right.
Mm-hmm.
C, the drag coefficient doesn't equal the Reynolds number.
No,
Yeah,
no.
it's just
One more time. So,
you have
oh, this is my mistake. No, sorry. I forgot. That's what I meant. Thank you for pointing that out. That was a typo, that was a mistake. Please correct that. Yeah. It's not equal to, it's functional. And we are now trying to do an experiment to find out what's that function. When the Reynolds number go up, does the drag coefficient go up or go down, and by how much? And why we are interested in this rather peculiar Reynolds number of 5 million, and why, with all that said, why do I put dimples on the golf ball? All right, and that's the direction we are heading. So the rest of the experiment, you can do it in air, obviously, it's a little easier. And you see a shape that the drag coefficient keep coming down with the increasing Reynolds number. And for some reason, at 5 million, there is a sudden change, a sudden drop, just a vertical decrease of Reynolds number at 5 million, of which I can reduce the drag coefficient by almost a factor of 2, from 0.5 to 0.2. Why? And how do I take advantage of that? If I hit a golf ball, for most people, any golfer here? Right? I mean, typically, you don't generate a golf ball with a launch velocity well over 100 miles per hour. I mean, that's more like a pro. So if you were me, I would hit the golf ball, I don't know, 60 miles per hour, 170 yards. If I apply that Reynolds number on the speed at which I launch the golf ball, I will be on the left. I'll be on the left of this Reynolds number. Okay? And that's for the case if I hit a smooth golf ball, no dimple. And why would that sudden change in the Reynolds number due to the dimple? What happened is, if I can put dimples on the golf ball, I can fool the boundary layer to make it think, because of all that roughness on the golf ball, I can trip the boundary layer to make it behave as though it's turbulent. And all of a sudden, I'm taking advantage of that more energetic boundary layer. And it turns out when I do that, I can have a form drag or pressure drag reduced significantly, where the overall drag coefficient is reduced by a factor of 2. So all those are just background. Now then let me fill in the more detail as to what I meant by all that. So the region lower than lower than 5 million, the boundary layer on the golf ball, by and large, is laminar in nature. What do I mean by that? So I have a golf ball where the flow is perpendicular to the axis. A boundary layer develops, and as the flow goes up to the 90-degree sector, I would experience a severe, very high, at worst, bad thing, pressure gradient. It's just because of the flow trying to move up this mountain. All right, so that severe, at worst pressure gradient will eventually cause my boundary layer to separate. And for a laminar boundary layer, the separation point is about 80 degrees. And that's shown experimentally. So I have both the lower and upper wall of the boundary layer peel off, resulting in a region behind this sphere where the velocity is very low because they have separated flow in what I call a wake. A region of relatively low velocity flow that also had relatively low pressure. turns out because of this relatively wide low pressure region or wake, I have relatively large form drag. The pressure difference between the front and the back is now what come into play in terms of the drag coefficient. However, if the Reynolds number is large, if I launch that golf ball even on a smooth one, well over 5 million, the boundary layer will become turbulent at the onset. So for a turbulent boundary layer, you have now a relatively different separation point. So the only difference is now the flow velocity is higher. I go from laminar to turbulent, same size sphere, same geometry. The separation point, simply for the fact the boundary layer has more energy, it's more randomness, has more unsteadiness to fight against this adverse pressure gradient that try to push me back. The separation point is much aft than 80 degrees. And what people have shown is more like 120 degrees before the boundary layer will peel off and separate it. So the comparison of the wake between laminar and turbulent is that you have a much broader and wider wake with a low region of pressure versus that of turbulent where the wake has shrink, becomes smaller. And the pressure differential between the forward and the aft lead to a smaller form drag or pressure drag. And that is the reason why there's a sudden drop, a factor of 2 in the drag coefficient. So what we do on the golf ball, in the case of the golf ball, is you put dimples on it, or way back they put sand on it. The sand being so irregular on the surface as the boundary layer go from the nose at 0 degree and up, as they go through those bumps,